Let's discuss about alcohol's preparation and then chemical reactions. Alcohol, see, first part of the alcohols are very simple. These are all repeated reactions. So that's why I'm directly showing you the reactions. Check out. If you have uh, alkanes and you want to convert alkanes into alcohols, then you better use alkaline KMnO4 and OH minus. Got it? So that will convert a tertiary butane into a tertiary butanol. Got it? No mechanism required here. So this and manganese will convert into MnO2. That's it. Hmm. Next, with alkenes. Alkenes, if you remember, we can do simple hydration, that is following Markovnikov's rule. So this will follow Markovnikov's rule, Markov rule with rearrangement, with carbocation and rearrangement. So this we have already learned that first a carbocation will form, it might rearrange if needed, then water will attack, converts into alcohol. Next, if you have oxymercuration, demercuration, here also we can have same Markovnikov addition. Mercury will form a bridge, water will attack on the more substitution, and then NaBH4 minus will give H minus here. So this is following Markovnikov's rule, right? And without rearrangement, without carbocation and rearrangement. Next, the next reaction is hydroboration oxidation. B2H6 will also make a boron attack here, and then hydrogen will attack back here, and thereafter OH minus will eventually come at this position, giving a 1 degree alcohol. So this follows strictly anti-Markovnikov addition. It is also without carbocation and rearrangement. One important aspect in here is it is going to give you syn addition. It is going to give you syn addition of H plus and OH minus. For example, let me show you here. In case if you have a methyl double bond here like this, and then I'm treating this with B2D6 in the presence of H2O2 and OH minus, then the products which will report will be like this. If methyl is here, then hydrogen should be here like this, and the added groups would be going inside. One is here we will get deuterium, and here we will get OH. This is a product. The other one will be its mirror image like this with right with uh, deuterium here and OH here, methyl here and hydrogen here like this. So you will get syn hydroxylation in this sorry, syn hydration. This is hydroboration oxidation. Next, if you treat with X2, first X will form a bridge form, water will attack here, you will get this halohydrin. This is called halohydrin. Halogen is also there, hydrogen is also there. And halohydrin, you can replace this X with NaOH, convert into alcohols. Okay. Now this is a set of new reaction you can see. In case if you have selenium dioxide and water, and you have an allylic position of carbon, then OH will be substituted on that position. So for getting an allyl alcohol, this reaction is specifically used. See, how the mechanism takes place here. Check. First, pi bond will attack on selenium because selenium has empty orbitals. Seeing that this pi bond will try to take the H plus because this hydrogen is sufficiently high acidic because of the hyperconjugation, and that makes the bond to push as a double bond, and you will get this form. Okay, and then the second oxygen now will try to attack back onto the double bond because selenium will pull the electrons here, pushing the double bond towards the other side of the carbon. So you will get this form. And now water will attack on selenium, and this bond will break onto O minus, and O minus will take H plus, convert into alcohol. So oxidation state of selenium is changing from plus 4 towards plus 2. Okay, so this is an allylic uh, oxidation. Now, if you may have noticed the mechanism carefully, the allylic carbon, if it is isotopic, it is the same carbon on which the OH is eventually coming. Check out carefully. Done. Right. Next. Next one is oxo process. Oxo process is basically making carbon monoxide and H2 to add. But what type of addition you will make? You will make an addition of aldehydic form and H minus form. So just like in electrophilic addition reaction, which means you will take the pi bond to go add onto CHO plus and H minus to add onto this carbon plus, and that's how you will get this product. Once you get an aldehyde, use catalytic reduction by H2 and nickel. You will convert that aldehydes into alcohols. So oxo process is first making of aldehydes and follow up to convert that into alcohols. Okay, next. If you have an alkene like this, same logic, pi bond will go attack on CHO plus and H minus will come on this position. Thereafter, H2 by nickel will give you this product. This is oxo process. Now, how do we get it from alkyl halides? Alkyl halide, when you react with aqueous NaOH, OH minus will attack, X minus will leave. As much as methyl is concerned, 1 degree is concerned, allyl, benzyl, these groups are concerned, you would usually do it is more favorable by SN2. While if you have RX reacting with water, it will always favor SN1 mechanism unless it is primary. Correct? On primary position, it is very difficult to get halogens. So 1 degree alkyl halides, okay, with H2O, very slow process, okay, and 2 degree, 3 degree alkyl halides with water, correct, this will be fast and reaction happens via SN1 mechanism. And lastly, if you have 2 degree, 3 degree RX with H2O and follow with AgNO3, this will become even faster or rapid. Why? Now AgNO3 is almost catalyzing the reaction because here the minute carbocation is trying to form, Ag will take X and convert that into a precipitate AgX. So because of the precipitation of halide, the reaction proceeds faster in the forward direction. Therefore, with water, when you have 3 degree allyl benzyl, reaction will happen very rapidly if at all we take AgNO3. Okay. So whenever there is an AgNO3, you will check out for a stable carbocation formation. Okay. Right. What role aqueous NaOH does? The same role moist Ag2O will also do. So moist Ag2O can also be read very similar to that of aqueous NaOH. And here again this will catalyze because silver will take halogen, converts into a precipitate. So if we have, in this case, rate is R1 and here rate is R2, then rate of R2 will be faster than R1. That's it. Okay. So whether it is SN1 or SN2, if you take silver salts, usually it will catalyze the reaction. Got it? Next. How do we get alcohols from primary amines? When you have 1 degree amine, when you have 1 degree amine, 1 degree amine, when you react with diazonium, NaNO2 and concentrated HCl, which will give you nitrous acid, it will convert that into alcohol and N2. See, NaNO2 plus HCl will give you HNO2 plus NaCl. And HNO2, if you notice, oxygen will take proton here, convert into OH2. OH2 is a good leaving group. It will go create an electrophile, nitronium ion. Thereafter, lone pair of nitrogen will attack on it. And this oxygen and these two hydrogens will come out as water, convert that into a diazonium salt. The structure of diazonium salt will be N triple bond N plus. This is how it is formed. And you see diazonium salts are extremely unstable if they are in an alkyl form. So because in alkyl form, Rn2 plus does not have any other motivation to remain as this form, it will immediately convert into R plus and N2. This happens because of a very strong bond dissociation energy of N2. But if it was aryl group, in aryl group you will notice that the pi bond will be in resonance with N2, and because of which it will stabilizes up to 4 degrees. Of course, above 4 degrees even that will also be unstable, but up to 4 degrees this will remain stable. That's why benzene diazonium chloride, benzene diazonium salt, we can isolate them at low temperature. But if you have any alkyl diazonium salt, we cannot regulate them. It is very difficult to isolate them. They will instantly react. Now notice, when you have a primary amine and react with NaNO2 and HCl, the major products that we expect are alcohols. You can get 1 degree alcohol and 2 degree alcohol. Of course, 2 degree is major because it will become a stable carbocation before water can attack. Now you might ask, sir, where is water? See, NaNO2, whenever we take it in an aqueous solution. And that we are adding it to concentrated HCl. Okay. So as you see, there is sufficient water in here. So that water is the one which will attack on the carbocations. Alongside forming, you will notice that there is chloride Cl minus also present in the solution. So Cl minus can also attack the carbocation at this position, carbocation at this position, because first you will get a carbocation for sure. So you will get 1 degree and 2 degree alkyl halides also. In fact, water can make elimination also like this. Okay, you can see this way. So sorry, like this way. If you have positive charge here, hydrogen here, H2O can attack here, remove this H plus, push it here to make a double bond. So that's how you can get an alkene formation also. Okay, so that's what you would notice here. Clear? And alkene will also form to a very small extent. Next, whenever there is an alcohol forming, this alcohol can attack on the existing carbocations and convert that into this kind of ethers. So it could attack on 1 degree also, you'll get this ethers. And 2 degrees can attack with each other like this. If you have an alcohol and a carbocation here, this can attack here and get this ether also. So these three ethers will also come as traces or minor product. Will come out as minor product here. Like, just a second, be on the line. So you can see these two alcohols are the ones which are usually going to come. Along with that, these are the traceful compounds which you can get, but they'll be in a very, very small quantity. I meant like this is a major product, approximately some 75% and above you will have. This will be around 24 to 25% you will have. This will all together will not be more than 1%. Okay, so you can understand that these are all extremely low concentrated products. But sometimes this kind of questions will be asked, what are all the possible products? When such language is used for possible products, you can write all of this 1, 2, 3, 4, 5, 6, 7, 8. These are all the possible products. Okay, next, notice if you have primary amine like this, react with NaNO2 and HCl, you get methanol and CH3CO CH3. Now, in this case, instead of methanol, you will get ethers as major product. Reason being, not lot of carbocation can be generated because this carbocation is not stable, and whatever the small amount of alcohol that is formed, that will keep attacking back on CH3N2, because here carbocation will not form easily. That's why an SN2 type of mechanism is favorable, and that brings the ethers as major product. That makes ethers as major product. Okay. Next, if you have this kind of amines, 1 degree amine, after removing NH2, you will get a positive charge, and this is a very stable carbocation. And that stable carbocation can show sigma resonance, which we call it as dancing resonance. Along with that, it can show ring expansion also. So this can also be observed. So which means you will notice that this, this, and this, these three carbocations will be available in the solution. So that when you react with water, you'll get an alcohol like this, and like this. In fact, CPM is a stable carbocation, so that would have major content. Then comes ring expanded form, and then comes this dancing resonance open chain form. Okay, percentages are mentioned in NCERT, so it's better remember that 48, 47, and 5%. Clear with these products? So this is what you will get it from amines. Next, with aldehydes. Okay, now this is the area from here up to the fourth one. All the reactions were repeated ones. Most of them we have seen it before. Got it? Now, look out from aldehydes and ketones. We learn thoroughly. From aldehydes, if you want to convert into an alcohol, we require two nascent hydrogens to add up, one here and one here. That's how you get alcohol. Same goes with ketones, which means, and you know that every a nascent hydrogen is equivalent to that of one electron. Therefore, two electrons are required for reduction to happen. Hence, you can see here two electrons are used, here two electrons are used. Okay. Now, when we do catalytic hydrogenation, whenever we perform catalytic hydrogenation, which means we have platinum, palladium, right? We write down palladium here. Platinum, palladium, nickel, palladium carbonated, and PtO2, which is also called Adams catalyst. All of these, when you treat them with H2, now this will become a reagent, and this reagent is what we call it as catalytic hydrogenation. See, when you have an alkene, when you have a ketone, react with D2, one deuterium will get added here, one deuterium will get added here. And because the addition is happening on a sp2 carbon, you know that this is an sp2 carbon. Since it is planar, the attack can happen from the top of the molecule or from the bottom of the molecule. Hence, you will end up getting a racemic mixture. In case if it is a chiral center, you will end up getting racemic mixture. Now, if you notice the usual reactivity, correct? Alkenes are extremely reactive towards catalytic hydrogenations. Then alkenes, alkynes, alkenes, then aldehydes and ketones. Okay, which means if at all we have, one pi bond outside carbon-carbon pi bond and one carbon double bond O, then H2 will get first added onto this position here. That is priority. So with one equivalent, this will be the product. But if you have not mentioned any equivalents, then you will reduce the hydrogen here also and here also. So you will end up getting alcohols in that case. Here everybody. And hydrogenation is also a syn addition, which means in case if you have a compound like this with double bond here and I make an D2 and PT addition like this, you know that it will make D and D addition like this. Okay, so it is a syn addition. This is just a recall well, so you know that this is always going to be a syn addition whenever there is catalytic hydrogenation. Okay, now let's look into complex metal hydrides. If you want to convert aldehydes and ketones into alcohols, then these two reagents are essentially used the most. One is lithium aluminum hydride, the other one is sodium boron hydride. If the question has simply even lithium aluminum hydride, you should understand the background that first we are adding lithium aluminum hydride with some ether solvent and then you are hydrolyzing it eventually. While when it comes to NaBH4, which means you are directly taking NaBH4 in ethanol. Okay. Now, when you add lithium aluminum hydride, you will see H will come here and H will come here. This hydrogen comes from H minus of lithium aluminum hydride, while this H comes from H plus of water. And when you use NaBH4, the H minus comes from NaBH4 and the H plus comes from ethanol. So this is how the reduction takes place. Now notice the typical mechanism with lithium. See, lone pair present on oxygen will first, try to attract the lithium plus. That increases the delta positive charge on this carbon. And that's when H minus as a nucleophile will attack. And AlH3 will be out. Oxygen notices that it can make a much stronger bond with aluminum because aluminum has more polarizing power. So lithium will be out, aluminum will be in again. And the minute aluminum gets a negative charge here, that can again become a reducing agent for the next molecule. So the same H minus attacks here when oxygen takes the next, this is the second mole. When the second mole of oxygen takes lithium, you will get like this. Again, lithium aluminum minus will attack on the third mole and subsequently fourth mole. So all the hydrates will be transferred to 4 moles of ketones. Ketones are aldehydes and you will end up getting this complex. Now this complex on hydrolysis, the O minus part will take H plus from here, convert into alcohols. So you would notice that we are getting 4 moles of alcohols, 1 mole of aluminum hydroxide and 1 mole of lithium hydroxide. And this is the overall reaction, 4 moles. So 4 is to 1 moles of reaction content we require to convert into 4 moles of alcohols. Okay, so I would suggest make a quick go through this, because this is an important area. From here onwards we'll be doing it thoroughly, so check out this properly with the mechanism and then we can go ahead. Take this example. If you have a ketone like this and you are reacting with NaBD4 in ethanol, then you know that you will get OH here and D here, and since it is a chiral center, you'll have plus and minus, so end up getting racemic mixture. You'll end up getting racemic mixture. Correct. So important, you should know that how exactly which hydrogen with deuterium is going on which particular direction. Same way, if I take a similar question and I add lithium aluminum hydride, followed by D2O, then we'll write the product as OD and H, again a chiral center, plus or minus, that is racemic mixture. Right? So you're not getting the same compounds, so you should know in which case where the hydrogen is going, where the deuterium is going. Okay, now let's compare, right? Compare lithium aluminum hydride and NaBH4. Right, you can say lithium aluminum hydride is more powerful reducing agent than NaBH4. Now what could be the possible reason for it? See here, we can see aluminum hydrogen, correct? Aluminum hydrogen have higher ionic character than boron hydrogen, and bond dissociation energy of aluminum hydrogen is lesser than bond dissociation energy of boron hydrogen. Now these two are the main causes, to make sure that lithium aluminum hydride relatively has more amount of reducing nature. The third important point is, okay, any polarized bonds we have like this, these kind of polarized bonds are more polarized, more polarized, with lithium plus as compared to Na plus, because oxygen makes a stronger bond with lithium plus as compared to that of Na plus. Therefore, oxygen, when it makes stronger bond with lithium, it will polarize the charge more and carbon will have more delta positive charge. Correct? And next, notice in isolated uh, alkene, right? Alkene present, isolated alkene present with aldehyde or ketone. then you will notice like this. Suppose I have a double bond O and H here and double bond here. Okay, whether we take lithium aluminum hydride or NaBH4, in both the cases, double bond is not disturbed. You'll get only OH and H and double bond will remain. So it does not make any impact on the double bond. So this is a major product. Got it? Keep that in mind. So double bond won't get disturbed in this case. Okay, but in conjugated in in conjugated system with C double bond O, okay, then what do you notice is like this. Double bond O and one double bond is present here. And again, the same thing. When you take lithium aluminum hydride or NaBH4, correct? You will end up getting two products. Okay, one is without disturbing the double bond, you will get an alcohol, which means H minus is getting added here, H plus is getting added here. So therefore, this is called 1,2 addition. This is called 1,2 addition. And the other product which you will get is like this, right? And this is 1,4 addition. So in this case, you'll have 1,2 addition and 1,4 addition. Usually, when you have an open chain and simple alkyl groups here, then 1,2 is observed to be major, 1,4 is observed to be minor. How is 1,4 happening? Let me show you conjugate addition. So let's see how the conjugate addition works. So when you have double bond here, now if you make a lithium aluminum hydride, that is AlH4 minus, then this H minus will attack on this position, pushing the pi bond here and pushing the minus charge here. So that way you will get O minus here, hydrogen coming at this position, double bond shifting here. Okay. So of course, if you add for another 3 moles of it, if you add another 3 moles of it like this, double bond O of 3 moles, correct? Because you can see that there is AlH2H3 also present here. So that will make it into 4 moles of it like this. We can have O minus this way. And this O minus group will be attached to aluminium 4 times. 4 times with aluminium minus. And this, if you treat with, because you have a O minus here, what you would notice is that that can undergo tautomerism. This can undergo 4 moles of like this with O minus and this way, which is present, that can undergo tautomerism and get double bond here and minus here. And this minus will be covered by lithium plus. Lithium like this, correct? Isn't it? So this is how you'll have 4 moles and aluminium is like aluminium plus 3 present here. Now this 4 moles of compound can be reacted with one more lithium aluminum hydride, correct, to get this into O minus, and here you can have this O minus, lithium plus here, and hydrogen will be here, and this 4 moles with aluminum that will be present. And thereafter, when you hydrolyze it here, you will get hydrogen at this lithium position also, and this OH position also, like this. Of course, lithium does not have plus charge here. I've just shown you for your reference. This is connected now, this way. So that is called as the first addition. What happened here, correct? Up to this is 1,4 addition. This is 1,4 addition. And last addition where this is has happened, this is 1,2 addition. Sorry, here. This is 1,2 addition. Okay, so 1,4 addition followed by 1,2 addition will give you this final product. So if the question is asked, only 1,4 addition is been given with one equivalent, so you'll end up only at ketone. But furthermore, when you reduce, it will convert into an alcohol form. Okay. Now you might wonder, sir, why 1,2 is major and why 1,4 is major. Okay. As of now, we'll not get too much details into that. Okay, because that will only take out a lot of time, but it's of no use for our problem solving. So remember more like cases here. The first case is when you have simple conjugated systems, then 1,2 is major, 1,4 is minor when you use lithium aluminum hydride or NaBH4. Got it? Next, if you have mm, next, in some cases, right? In some cases, double bond reduction predominates. Double bond reduction predominates. Okay. Again, this that's why I said learn it like specific cases instead of trying to go through the mechanism into it. Check. For this kind of a conjugate cases, if I treat with NaBH4, okay, if I treat with NaBH4 in ethanol here, it was been found that the entire reduction will happen and you will get this as 1,4 addition followed by 1,2 addition. 1,4 addition followed by 1,2 addition, and this is 100% product, so there is no other minor product into this. While if I take the same compound and treat this with lithium aluminum hydride followed by H2O, got it? Then I was getting two products, that is OH here with double bond, which is major, which is 1,2 addition as usual how we have seen the earlier case, and then we have 1,4 addition which is minor. 1,4 addition followed by 1,2 addition. Okay, this is the next case. Okay, same thing. I'll just write back to back here so that you can have a clear reference in that. So same kind of question. If at all I have it with cyclohexenone, then with NaBH4 followed by, I mean, in ethanol, correct? This was giving two products this time, OH with double bond and 1,4 addition here. Okay, so this is only 1,2 addition. This is 1,4 addition followed by 1,2 addition. Okay, and this was found to be approximately 51 percentage and 49 percentage. 51 percentage and 49 percentage. Okay, similarly, if you take this compound react with NaBH4, correct? But NaBH4 in the presence of cerium chloride, and then, it is happening in ethanol. In that case, it has been found that 1,2 addition is almost 99 percentage, is 99 percentage, and 1,4 addition is only 1 percentage, is only 1 percentage. Why that is happening? Reason could be the cerium will try to make, sorry, cerium will try to mask the double bond here, and then BH4 minus will only focus on reducing this 1,2 position. So here cerium plus 3 is masking double bond. Okay, so this is called as Lush reduction. Clear? So compare that, with 5-membered ring and 6-membered ring, how the reactions happen in both the cases. Okay, go through it once quickly. I'll give a minute's time. Check all conjugated system, what is happening. Let's see the next case. Okay, the next case is called cinnamic systems. Cinnamic system is when you have benzene with CH double bond CH, C double bond OH, sorry, C double bond OH. This is called cinnamaldehyde. Cinnamaldehyde. So cinnamaldehyde, when you treat this with lithium aluminum hydride, what has been noticed is it will primarily give 1-degree alcohols. It will give you 1,4 additions. You will get this as OH and H. Complete 1,4 addition followed by 1,2 addition. And it is noticed that it is almost 100% in this case. Okay. But the same reaction, if you operate with lithium aluminum hydride, sodium boron hydride, sorry, NaBH4, this time it is giving 100% only 1,2 addition. 1,2 addition. Alright, so that is the difference you will notice. Lastly, the same cinnamaldehyde, if we react with H2 in the presence of palladium and methanol, right, mix of it, and at around 25 degrees Celsius, it has been noticed that it will only give you 1,4 addition. Sorry, only give you 1,2 addition, but that too at alkene. It will not disturb this alcohol at all. So this is a product form. 100% only this product. So this is a cinnamic case, a very special case. Operates extremely different, completely different with different reagent. With lithium aluminum hydride, 1,4 followed by 1,2. NaBH4 completely 1,2. And with H2 and palladium, not even touching the aldehydes and ketones here. Correct? So this is the cases which you'll notice with cinnamic acid. So this page is dedicated to mainly those cases, everybody. So you don't have to worry about, what is the background behind it. Just remember it like cases. That's all. Okay, now let's see. Next reaction is with diborane. Diborane reduction reactions. All right. So overall reaction is like this. If you have an aldehyde or a ketone, and then if you are reacting with B2H6 in THF, that is hydroboration, if you may recall, followed by hydrolysis. In that case, it will end up getting as alcohol. Okay. Same way, if you have ketone, and sometimes instead of writing it as B2H6, it is simply given as BH3. Sometimes it is directly given as BH3 and then followed by hydrolysis. That will also give you alcohol. Okay. Now, if you notice the mechanism, what are the steps that are taking place here? So first, double bond O will strongly attract BH3, and that will make this as O, B, H, H2 minus, and here you will have plus charge. So you would see this H minus will attack here. So that makes it O, B, H2 and H. Correct? Again it got empty orbital. I'm sure you remember the hydroboration steps. The same logic to be applied here as well. So that means another 2 moles of aldehyde or ketone, if you take it, they all will attack on it in the same way. You will get oxygen with boron, oxygen with boron, oxygen with boron. So you will get this as triisopropoxy borane. So trialkoxyborane. So we'll get a trialkoxyborane in this case. And this trialkoxyborane, when you treat with water or in acidic hydrolysis, you'll get 3 moles of alcohols plus boric acid, BOH thrice. That's how you'll end up getting alcohols. Okay. So I hope the mechanism is very simple, straightforward. Okay. Now if you notice the reactivity order, this is a very strange order. You'll see acids are extremely reactive in this case. Then comes ene, then comes ine, and then comes aldehydes. Okay, aldehydes and ketones. Correct. And after this, then comes, any ester form or acid chlorides. Okay, least reactive. These are least reactive. So very strange order. I'll explain it as we go ahead why that order is. All right. But for now, our discussion should be about ene comparison to aldehydes. Between ene and aldehyde, you can clearly notice that enes are always more preferable, which means suppose if you have an aldehyde like this and I take one equivalent of BH3 and one equivalent followed by hydrolysis. So you will only reduce this part. You will keep it like this. So H and H will get added. This is the product you will report. Clear? I hope that is understood. This is diborane reduction. Next. The D part we will learn is dibal H. Dibal H. Okay. In dibal H, you will see. Okay. Dibal H is a reagent which is used. Basically, the name is diisobutyl. Diisobutyl aluminium hydride. So It is little bit more uh, branched and more bulkier as compared to that of lithium aluminum hydride. And lithium aluminum hydride has four hydrogens. Here we have only one hydrogen. Structure wise, this is how it looks like. Correct. We have aluminum with one hydrogen. So this is divalent. Usually this exists as dimer. This usually exists as dimer. That is aluminum with R and R, aluminum with R and R here, and you will have this hydrogen at the bridge position like this. This is how it exists. Got it? Reaction wise, you will notice that C double bond O Ne R dash, that means ketones are aldehydes with dival H. Dival H will make it reduction to OH and H R dash. Okay, but this is at normal temperature conditions. Got it? But the same reaction, if you notice, that is dival H at minus 78 degrees Celsius or below. In that case, no reaction. That means alcohol formation is subject to temperature. If the temperature is room temperature or above, then the reaction of aldehydes and ketones to reduction will happen. But if it is at a low temperature, then the reduction is not observed. Okay. So I think this part is clear. What does dival H do? Next, E. E is uh, by dissolved metals, by dissolved metal reductions. See, in case if you have a ketone here like this, you have R and R dash, and that when you react with sodium in liquid ammonia, sorry, sodium plus liquid ammonia, which we usually call it as Birch reduction, or lithium with liquid ammonia, or you can have sodium in ethanol. Now, out of these three reagents, the sodium and ethanol is the one which will be using the most. They all will again help in getting a reduction done with OH and H and R dash. This is the product form. See the mechanism here. So let this as R, C double bond O, R dash. An electron has to go attack on this carbon. Let this as RCO minus. Single electron will be present as a radical. Got it? Clear? And from ethanol, right? From ethanol here, O minus will take H plus and convert this into RCOH, and that radical form will remain. And here, next electron will enter, convert that into carb anion minus and R dash. And again, this reacts with ethanol. This reacts with ethanol, takes H plus, and that's how it will convert into OH and H. So both hydrogens are coming from solvent only, but electrons have been added in between. Correct? So this is how the dissolved metal will convert aldehydes and ketones into alcohols. Clear? Please check this out quickly. Right. So see this. Now how the questions can be asked from here. Let me put some examples here. Check. In case if you have a ketone here with double bond here in a conjugated system, you will get 1,4 addition when you take sodium in liquid ammonia. Sodium in liquid ammonia. So it will get complete reduction. So you will get this as OH. But if it is isolated like this, is isolated liquid ammonia, then the double bond will not get disturbed. Only reduction of ketones will take place. Or if you have a triple bonded system like this, we have a double bond O and triple bond here like this. Then we have sodium and liquid ammonia. On a triple bond, you'll get a Birch reduction done. You know that Birch reduction will make it into a trans alkene, and here you will get alcohol. So this is where it will end up. And if you have double bond O here and triple bond at a terminal position, at terminal position we cannot do anything with liquid ammonia. It will only end up having like a salt form here, and this will get reduced, and you'll simply have C minus Na plus like this. So you can see the distinction at which location what is the product you will get. If you have an alkene or alkyne along with aldehydes and ketones, so you should know what is the product. Done. This is about metal reduction. Next, check out MPV reduction. MPV reduction. Okay. Name is Mervyn Horndorf and Warley reduction. Usually, what we do, we will have here two ketonic forms, right? Sorry, one ketone and one alcohol form that on reaction with aluminium isopropoxy, that is IPRO thrice with aluminium. This is aluminium isopropoxy. That will convert the ketone into, that will convert ketone into alcohol this way and alcohol into ketone. This is the reaction that happens. Correct? The reverse reaction is called as Oppenhier's oxidation. This is Oppenhier's oxidation. Okay. Now let me show you the mechanism. See how the mechanism happens here. Aluminium isopropoxy, which is let me write this aluminium isopropoxy as IPRO here, okay, and other side I'll actually show the structure. This is how propoxy is. Isopropoxy oxygen, correct? Isopropyl oxygen. And now we have ketone, which is C double bond O and 2, like this. This is the ketone which we have, right? So the lone pair present on ketone will try to attack on aluminium like this. And as it attacks, you will notice we will get aluminium with isopropoxy. Here also we have isopropoxy And here we have oxygen and carbon, which has a double bond here with two R1 and R2 group, correct? And which gets positive charge here. Aluminium will get negative charge here, and that has oxygen and hydrogen with two methyl groups, correct? So on this carbon we have a hydrogen also, right? So that is the hydrogen I'm talking about. Let me mark that hydrogen for reference. This hydrogen and this hydrogen is same. Okay. And now what will happen? Internally, you will see this H minus can attack on carbon. This bond can move on oxygen here, isn't it? And that will create O minus on that oxygen here. And this bond, uh, oxygen here, and yeah, this bond can push into making a double bond form, right? So by which you will see isopropoxy connected with aluminium, another isopropoxy, another isopropoxy. Here it is connected with oxygen, with C, hydrogen, and R1 and R2, and this has departed as ketone. Correct? This has departed as ketone. Now, this compound, again, when you react with an alcohol which we have taken, check out, this is the alcohol which we have taken here. Correct? This is alcohol which we have taken. And now, the lone pair present on this oxygen will attack on the aluminium here, correct? Attack on the aluminium here. And as it does, we'll see the product will be something like this, where we have O and H here with a plus charge, and this way. So now obviously this oxygen will try to take the H plus from here and convert itself into alcohol. This aluminum has minus charge on it. So that's how again it will convert into aluminium isopropoxy, and other side will get R1, R2, and with OH and H. Okay, again let me point out this hydrogen and this hydrogen is the same, while this hydrogen which I have marked it earlier, that is the same hydrogen. Okay, so that you are clear about which hydrogens is going where. So this is how you can get an alcohol. Okay, so you can see this compound and this compound. This is the reduced and oxidized forms. Please go through it carefully. You can see this above reduction, everyone. The above reduction, above reduction is highly selective for aldehydes and ketones only, and does not impact other functional groups. That's why MPU is specifically used when you want to only reduce aldehydes and ketones. Correct? Next, GC reduction of acids, carboxylic acids. Got it. So first, acids and derivatives. We'll write down this as acids and derivatives. That is acids and its derivatives. So first one, We'll start with carboxylic acid. So if I want to convert carboxylic acid into alcohol, RCH2OH, got it? Then notice the oxidation state. Oxidation state here is +3. Oxidation state here is -1. So there should be 4 electrons transferred. Okay. And if I take H2 plus Pt, Pd, nickel, PdC, correct? Or PtO2, correct? Then it is been noticed that none of this will help in reduction of this one. Instead, none of these will help. Instead, we'll have to take H2 by, correct, uh, ruthenium with carbon activation, or right, this, or we can take barium, copper and chromium mixture, or we can take copper chromite, Cu, copper chromite, okay, Cr2O4. This kind of a mixtures we need to take. Then only we will be able to reduce the acids into alcohol. So if this is the reducing agents, in such case acids RCOH with these reducing agents can be converted into CH2OH. Okay, this is the first set, correct? Second reaction where uh, carboxylic acid can be used is if I take carboxylic acid and react with NaBH4. Now simply first an acid base reaction will take place and you'll get 4 moles of RCO minus Na plus, and you will get 4 moles of H2 gas. That's it. And further reaction with NaBH4 will not be successful. You will not see NaBH4 will make any further reaction. So if you are expecting alcohols to reduce to acids to reduce to alcohols, then NaBH4 is not a correct reagent. Okay, next, if I take 4 moles of acid and react with lithium aluminum hydride, then definitely here an acid base will happen first, RCO minus Li plus, and okay, Li plus and Al plus 3 also. So I'll just write on this as 4 minus Li plus Al plus 3, and that plus we will have uh, we'll have this as 4 moles of H2. And this, if now further reaction with lithium aluminum hydride is actually fetching 4 moles of alcohols, RCH2OH and AlOH thrice, like this, and so on. So how come it is happening in lithium and not with sodium? So in NaBH4 this reaction is successful, but with lithium aluminum hydride it is successful, but with NaBH4 it is not able to do it. Now just see the mechanism. So when you have R C double bond O, got it, and we have O minus here. Okay, so after release of that H plus, this O minus basically is in strong contact with Al H2 minus, like this, correct, H3, after releasing one H plus H2 gas. This is how the first mole has been reacted. Now within the first mole, now see this case here. This one will have RC double bond O with O and Al, H and H here, correct? So this bond will try to push it back towards aluminium, right? And that will push the H minus here. Mhm. One second. Oh, sorry, I didn't push the hydrogen first. Yeah, here we have minus and hydrogen here. So this H minus will be pushing it here. That will make it RCO minus hydrogen with O Al H2. And as this pushes, you'll get this as O minus. And now you can notice this is converting into an aldehyde form. And you'll get this as AlH2O minus. AlH2O minus. Correct? And of course, the minute you get this as AlH2O minus here on hydrolysis, right? So once you get this as an aldehyde, again you can see RCH double bond O plus O minus with aluminum H and H here. So this H minus can attack here and this O minus can attack back on aluminum. So you will get this as RCH oxygen with Al H and O minus, and here hydrogen will come. And this on hydrolysis will be able to convert that into RCH2OH and AlOH twice and hydrogen. Correct? And of course, furthermore, this hydrogen can also be utilized. So stoichiometrically, if you notice, right, let me show you the stoichiometric ratio. If I take 4 moles of acid first, I require 1 mole of lithium aluminum hydride to first convert this into 4 moles of RCO minus and 4 moles of H2. 4 moles of H2. And then again 4 moles of RCO minus. When you react with 1 mole of lithium aluminum hydride, it will convert into 4 moles of aldehyde, correct? And again 4 moles of aldehyde. When you react with 1 more mole of lithium aluminum hydride, will eventually form 4 moles of alcohols, right? This way. So now if I write the overall reaction, everybody, check out the overall reaction. The overall reaction is 4 moles of acid plus 3 moles of lithium aluminum hydride. That will eventually get 4 moles of alcohols, correct? And 3 moles of aluminum hydroxide and 3 moles of lithium hydroxide plus 4 moles of hydrogen, right? So stoichiometrically, this is the balanced equation. Got it? So overall, this is the reaction that is happening. I hope all of you got that. How lithium aluminum hydride is able to reduce the acids. Unlike sodium boron hydride, lithium aluminum hydride can do this. Please check properly.